First question is basically descriptive. It's not descriptive, it's a definition based question. What is the p-value? So it is the probability of observing so in the statistic what you do is you have some samples, you sample from some unknown distribution, and you estimate the parameters of this particular distribution from the given samples, right? That is the basic tenets of the statistic. Now p-value is whatever the sample you have observed. There are also samples which are actually more extreme than the observed sample. So you consider sum of all such probabilities of those samples, and that will be your p-value. So in terms of graph, if you see that you assume certain null hypothesis first of all, okay, and you consider the graph or a probability density function under the null hypothesis. That means you have assumed certain distribution. Now you are observing certain sample, let's say this particular green sample. So what are the sample which are as extreme as the green sample? All such right hand side extreme and left hand side extreme, all are as extreme as the green sample. So the probabilities of all such samples is called as a p-value. Now another thing is p-value should also be calculated in conjunction of the alternative hypothesis. So it might happen that your alternative hypothesis is, so your null hypothesis is mu or a mean is mu, and your alternative hypothesis is mean is strictly greater than mu. So in that case you only consider the probability of the right hand side region, because your particular test is only one tail test, right? So you only consider right hand side region, and that will whatever the probability that you get, that will be your p-value. Don't consider both tails. It is extremely important that depending on the alternative hypothesis, you consider the extremes of both tails, or extremes of left tail, or extremes of right tail. It's important that whatever the value that you have calculated is dependent on the alternative hypothesis. So we'll see certain question like that. In the last lecture, I have discussed certain question which is related to, I would say, this particular question. So you have 6 size samples, and in last particular video I have some null hypothesis half. Here also null hypothesis is half. In last video the alternative hypothesis is theta is strictly greater than half. Here the alternative hypothesis is theta not equal to half. So this is two tail test. Earlier we have whatever test we would have done was right tail test. So the setting apart from this is everything same. 6 binomial samples are there. Y is a binomial sample, and some y is sum of x1 x2 up till x6, and what will be the p-value if y equal to 4, right? But the alternative hypothesis is not equal to here. So if I draw the corresponding graph of this particular binomial sample, so just actually it's a discrete random variable, but I am drawing the corresponding continuous counterpart of this particular binomial PMF. Right? So if you see that if you observe 4, you will also add 5, because 5 is extreme than 4, 6 is also extreme than 4. Then you will also add a probability of y equal to 2 as well, probability of y equal to 1 as well, probability of y equal to 0 as well. Earlier you were not adding those particular values. These values you were not adding. But now you will add it, because the corresponding alternative hypothesis is theta is not equal to half. Null hypothesis is theta is equal to half. So under the null hypothesis, this is my orange curve, that is my distribution. But the p-value that I am calculating the samples of probabilities of the samples that are coming under the both extremes. So if you just simplify this, you will get the 11/16 as the answer. So consider this question. Based on same sample data, 90% confidence interval will be wider than 95% confidence interval. If the data is strongly skewed towards right, mean is typically smaller than median. Basically both statements are false. So first of all, you need to understand what is the confidence interval. So in a statistic, you have some samples, you get some sample estimate, and you want to know region under which the original parameter falls, right? So let's say you want to estimate the mean, right? So you sample some data points and you actually calculate the mean. That is typically called as a sample mean, and original mean is original parameter, right? Now please see, whatever the original, let's say mu is your original mean. So let's say I draw a certain normal graph of mu. Okay. So everybody should know that through the central limit theorem, the sample mean is actually normally distributed across the original mean. So this is my central limit theorem statement only. There is nothing more. So confidence interval is what? The difference between, or the distance between. I want a region such that I am 95% sure that difference between original mean and the actual mean is at most this. I want to be 95% sure. So basically I want region under this two particular region, right? I want a region. So under the mu, let's say mu is certain parameter. So I want these two sides of the mu. What I can say, this particular shaded region of under the pink color covers a 95% probability, and under the green color covers the remaining 5% probability, right? So 90, that means what? The difference between original mu and the sample mean is actually half of the length of the pink region, right? So difference between original mu and the sample mean is actually at most half of the pink region with 95% probability, if I know the pink region covers 95% of the probability, right? So if you consider the corresponding value, this is 1.96 and this is minus 1.96. Between these two, this particular entire curve covers 95% probability. So this is the standard normal curve actually, considering the variance is equal to 1, right? So now you have some sample variance, and as you go on and on increasing your confidence, that means you are actually increasing the length of the confidence interval. So 95% confidence interval will not be smaller, it will be actually larger. And if your data is strongly skewed towards right, so in a very simple case, it can happen that data is equally skewed or centered around the mean. Now it can happen that if data is sampled around the mean, then mean is same as median. Everybody should know that. If it is perfectly symmetrical around the mean, then then mean is same as median. But some probability from left hand side, if I take and I make the right hand side samples as a more probable, then what might happen is I will have a more and more sample with the larger value. That means my mean will increase. But if I order the samples in the sequence, still the middle element will actually be shifted towards left, not right. So the median element will be shifted towards left and mean will be shifted towards right. That will imply that mean will be actually higher than the median, and second statement is actually exactly reverse of what is true. So 2 is false. So this, you can visualize the confidence interval as well like this. So according to the various levels of confidence interval, various Z multipliers are also given. Z is nothing but the standard normal. Okay, standard normal random variable, 0 mean and 1 variance. That is the Z. Let us consider this question. This is also actually definition based question. So many things you should know in the statistics. Some definitions are only there. So what we do in the statistic, there is some null hypothesis. There is some sample that we get. Now, according to the sample, I may accept the null hypothesis, reject the null hypothesis. Then the significance level indicates that the maximum level of or a maximum error of a type 1 that I can tolerate if null hypothesis is true. So when the type 1 error occurs, if I reject the null hypothesis, I will have a type 1 error if the null hypothesis is also actually true, but I am rejecting it. So then the type 1 error occurs. So let's say I'm doing one tail test. The same analogy can be replicated in two tail tests, but let's say I'm doing one tail test. I'm observing certain sample, or let's say I'm not observing certain sample. No sample has been observed yet, but I'm okay that if the null hypothesis is true and I'm still rejecting 5% of the time, I'm okay. That means what? If my sample belongs to any of this region, and if the green region is actually 5% of the probability, then I can actually consider rejecting the null hypothesis, and I can say that okay, 5% of the time I might make a type 1 error, but 95% of the time I will not make the type 1 error. This is only for one tail test, okay? Otherwise I have to consider the probability of both the sides. This is only for the one tail test. So probability of the significance, this is called a significance level, right? 5% significance level means what? Maximum accepted probability of type 1 error. Type 1 error, type 2 error, these are extremely crucial definition in the statistic. Type 1 error means, we have discussed this in the last lecture, so I am not writing it. Type 1 error means error that you make by rejecting the null hypothesis even if the null hypothesis is true. And type 2 error is you are unable to reject the null hypothesis where it is actually false. So that's why significance level is also called as a maximum accepted probability of type 1 error, and it is also called as a sometimes critical region also, right? So size of the critical region. Critical region is the region under which your sample falls and you are rejecting it. That is your critical region. So please be very clear of this terminology. Critical region is actually depicting the region. Significance level or significance probability indicates the probability under which you can tolerate the type 1 error being occurred. And size of the critical region is actually nothing but the significance level. Size doesn't mean the length. Please don't, it seems confusing, but typically this word has been used. Size of the critical region, that means significance level only, right? So size of the critical region is that. The critical region has already been defined, but still the sample has not come. So now let's say I put the sample, and let's say it gets into the critical region. That means you will actually reject the null hypothesis, but you will first calculate the p-values, right? So with respect to this particular sample, these p-values are actually probability of all such samples equally or less likely than the observed samples. Now obviously p-value is actually less than the significance level. That's why you actually reject the null hypothesis. It can also happen that the observed sample actually falls out of the critical region. In that case you will not reject the null hypothesis. That is, in that case p-value will be higher than the size of the critical region or the significance level. These three terminology, p-value, size of the critical region, significance level, right? Basically size of the critical region is nothing but significance level only, right? And critical region indicates the region under which if your sample falls you will reject the null hypothesis. C is the correct answer. Okay. Now this is a question related to confidence interval. Interesting question. So wine under the bottles, the liters or the volume of wine under the bottles is normally distributed with some mean, and variance is 25, right? Now you need to check the minimum number of bottles. You need to ensure that the confidence interval with the width less or equal to 1. This is interesting. How the confidence interval has been calculated? 95% interval, 90% interval. So if you see our previous question, confidence interval with respect to various confidence level, and the Z multiplier goes on increasing. But the formula of confidence interval you should know with respect to Z value. If you want to calculate the formula of confidence interval, this is my sample mean plus or minus Z multiplier corresponding to the confidence interval, let's say 95% or whatever, right? Sigma times square root n. So as your number of samples increasing, the size of the confidence interval length goes on decreasing, because it is inversely proportional to the square root of n right? So as your because you have more and more samples, so you can actually say that with more and more confidence that your actual samples are actually in a shorter length of the region. So this is the formula to calculate the critical region. X bar is the sample mean, Z is the corresponding Z value, and sigma by square root. Now there's something I need to make sure that this Z value, okay, so first of all let me just replace all the quantities. So X bar here has been, okay, whatever the X bar, I don't know, but the length of the critical region, or sorry, length of the confidence interval is 2 times Z 0.95 sigma by square root n. I think you have been given so this has to be less or equal to 1. So I need to calculate the n for which these things happens. Sigma is what? Sigma has been given, sigma is 5. So sigma is 5, so this is like 10 times some Z multiplier. Okay. Now this particular Z multiplier, how you will calculate for the 95% confidence interval? It is extremely important. You need to know this. Okay. So if you consider a standard normal curve, 0 mean 1 variance, as I have already told you, 95% of the confidence interval, what does it indicate? The difference between sample mean and the original parameter is at most this many length with 95% probability, right? So that's what I want to calculate. I need some value at which I can say that difference between sample mean and the original mean is, so let's say this is my sample mean, this is my somewhere original mean can happen, it can be happen left hand side but right hand side. So difference between sample mean and original mean, okay, so let's say you observe some sample mean somewhere here and this is my original mean. So difference between sample mean and original mean, 95% of the probability should be that it can be in under this particular region. So if I take this particular value, let's say minus 1.96 and plus 1.96, I can say actually this, that under the pink curve, the difference between sample mean and the original mean is half of the pink length, because it covers 95% of the probability. Hopefully it's clear. Because why I am considering this much length? Why I am considering this much length? Because this pink region is 95% of the probability, right? Now I have to consider both sides. It can happen that X bar can also fall into the left hand side of the mean also. But the difference between mu and X bar could be at most half of the pink length. So I actually want to find out what is the half of the pink length. What will be the half of the pink length? I will consider the critical region as minus times sigma. So this Z multiplier, that is Z multiplier is nothing but the half times pink length. Half times pink length. Right? So this is half times peak length only. So you just calculate the half times pink length for which value it occurs, half times pink length. Pink region is the probability that I am 95% sure that the difference between them is half times pink length. So for that you will consider a minus 1.96 value. There is also minus 1.96 and plus 1.96. So 1.96 is the corresponding Z multiplier. Okay, so it is important that you identify the Z multiplier correctly and you just simplify this equation. You get the n equal to, I think, 90, 20 or 19 or 20 is the correct answer. Easy to derive it also, So see, if I want to convert x bar, which are n samples or mean of n samples, in terms of standard normal, you can easily derive it with this. Mu is some, unknown mean. Okay, so this is my standard normal, normally distributed 0 and 1. Right. Now this is my standard normal. I need a region under which this particular normal random variable will fall with a 95% probability. Right. So that will be, I can say that probability of some value, let's say some threshold. So let me just say that z 0.95 is actually less than this particular random variable minus mu square root of n minus plus z 0.95 is equal to, so that's how the confidence interval is being defined. So this z value, if you just calculate it, this particular z value comes out to be 1.96 actually. So this is minus 1.96 and 1.96. So I'm sorry, I have made a slight typo here. Sigma over square root of n should come. That's how the standard normal will be defined. Sigma is some known mu, let's say, some known standard deviation. So you can say that with 95% of the probability, mu is actually greater or equal to x bar minus z value of 95% interval multiplied by sigma of square root of n, and mu is less or equal to whatever x bar plus z value of 0.95 sigma over square root of n. So this is my interval. From this lower side, this highest side. That's how we can. So please see, you identify the interval like this. So if you are facing too much difficulty of imagining it, you imagine this particular curve. So this is the curve. Right. So it will be 95% of the time the difference between mu and x bar should be half of the pink region. Okay. Or you can derive it by this particular way as well. That is also fine. So you make it the standard normal. I don't know the mu, but I'm interested in certain region such that whatever the standard normal is there is between this particular region. So for that particular value, the z value that we will get is 1.96. So this is 1.96 and mu is greater or equal to this with 95% probability, and mu is less or equal to this with 95% probability. So consider this question. It is simple. It is asking the z score. Sample mean is given. Original mean under the null hypothesis is given. Sigma is also given. N is also given. So you just simplify this equation and you will get it. So this 0.61 is the answer. So this is again the simple question. Some tabular form of the data is given. Certain mark is given. The corresponding number of students, that is frequency, is also given. So first of all, mode is the maximum number of times certain value is occurring. So you have 4 different values: 25, 30, 35, 40. 40 is occurring maximum, 35 occurring maximum number of times. That is mode. Median is you organize all of them in the lower to higher, and whatever the middle value is there. So if you organize it, there are 100 data. So 50 data point will be in the middle. So left hand side 20 data has a 25 marks. Then left hand side 20 to 40 data has a 30 mark, and 50th data point has actually 35 marks. So that will be your median. And mean is just this below formula. Frequency multiplied by the mark. You just sum all possible frequency and multiplied by the corresponding mark divided by total number of students, so that you will get the corresponding mean. So mean is 33. This is my equation. This is my equation of mean. So now this is an interesting question. So you are given xi y as a training data, or you have assumed some distribution of the y. Y is the logarithm of w of xi. Okay. And sorry, yi is normally distributed with the mean of logarithm of w of xi, and the variance is 1. And I have also given the corresponding conditional PDF as well, because most of the time student doesn't know the PDF formula of the normal distribution. It is important that you know that, right? 1 over square root 2 pi and it's e to the power this. But if you don't know that, I have given it in the question only. Now please see that you need to find the maximum likelihood estimates of the W. These are the very important concepts in the statistic as well as in the machine learning. If you remember the logistic regression, we have also derived with the maximum likelihood process. We will also derive with the some formula of the linear regression as well with the maximum likelihood process. But this is not linear regression because the form that has been assumed is somewhat different. So you are given certain data set of n points, let's say, and you want to estimate what is the parameter w for which these data points are maximum likely. So in the next slide, I have actually first written this particular Gaussian probability density function. This is for every yi, right, given xi. What is the w is unknown. So you need to find a w for which you have a y1, y2, so y1, x1, y2, x2, y3, xt. All such independent samples are being maximized. So how to do it? You create a likelihood function. That's what I have done. Create a likelihood function and you multiply all such particular probability densities. Ideally you should multiply the probability, but this is the continuous random variable, so you just multiply the probability densities and you try to maximize them. So that's what I have done in the next slide. And this is the likelihood function. Everybody should be comfortable with the likelihood estimation process. Okay, that's an important concept. Now this is the likelihood function. Please see that the function is non-negative. So instead of maximizing this particular function, you can maximize the logarithm of that function. That is also fine. So I have just taken the log and maximizing it. So I am just maximizing it over all possible w's. So this is actually maximizing over all possible w's. How to maximize over all possible w's? Only one parameter is there. So you just differentiate it and equate with 0. That's what I will do. Differentiated and equated with 0, and I have simplified some form, and I will see that this particular formula is arrived. Now you need to also check the second derivative is actually less than 0. Okay, because the only differentiating and equating with 0 does not guarantee you the maxima. So you need to also check the second derivative is also a second derivation test as well, such that whatever the final answer that you are getting is actually the maximum. So it's this is your final answer. Summation of yi is equal to summation of log of w star xi. So that's your answer. D is the answer. So you need to be comfortable with how I should do it is, see, there is some unknown parameter. You need to find the likeliness of that parameter. You have n samples. Right. So first of all, write the probability of that particular sample with some unknown parameter, right? In terms of you write that particular probability function, right? If you assume the binomial and with certain mean, then in terms of p and n you can at least write, right? So you write that particular function. You have n samples. Now you maximize over all such parameters the likeliness of the observing these n samples. So you just multiply all those samples, right? Why? Because observing n samples, the joint probability is actually multiplication of the individual probability. Why? Because these n samples are independent. It is extremely important you go through this particular lecture of maximum likelihood estimation if you are not comfortable with the process. I have uploaded 2 lectures and if you go through the logistic regression as well, that is also maximum likelihood process. So that also you can go through that lecture. It's important. Okay, you will be comfortable with the process. So I have done this. So but one thing I should mention is you please also check the second derivative test. Consider this question. So there is cigarettes is given, some mean is given, standard deviation is also given. From is coming and he's claiming that he has a lesser number of nicotine in the cigarette, and we are given some sample with some mean. So this is my sample mean 1.54. This is my mean under null hypothesis 1.6. This is my standard deviation that is known. 20 is the number of samples. You can definitely know that the claim is the null hypothesis is under the new cigarette the nicotine content is same. The alternative hypothesis is nicotine content is same, that means 1.6. Under the alternative hypothesis it is strictly less than 1.6. It is important that you identify the null hypothesis and alternative hypothesis appropriately. After you do that, you have some sample, you apply the Z test. What you do is find the corresponding Z score, which is this, and this is left tail Z test, because your hypothesis is actually testing that whether the new cigarette has a lesser number of nicotine content. So that's why it is a left tail Z test. So it's important it's mentioned here. This is actually left tail only, not two tail. Don't apply two tail Z test. It's a left tail Z test only. Consider this question. So there are two proof readers are there, and the hypothesis is assumed hypothesis. Okay, so I will come to the hypothesis later. Let's read the question. So somebody is claiming that A is superior than B. A and B are both are proof readers. That means a certain set of the scripts, they are actually identifying errors. It is said that 15 errors has been found by A, 12 errors has been found by B, 10 errors has been found by both. I want to give the p-value of this particular test, assuming the null hypothesis that both are equally competitive, and the alternative hypothesis is B is superior than A. So apologies for the typo in the question. I should actually mention that B is superior than A. This is my alternative hypothesis. Okay, this is my alternative hypothesis. Now, so this is my alternative hypothesis. So you are given explicitly whatever the hypothesis is that in the question. Now, what you do is you actually convert these entire samples in terms of Bernoulli random variable. Why? Because see, every error is there. Either it can be found by none. In that case, you can't actually assess about the competency. It can be found by both. In that case also, you can't assess the competency. But you can assess the competencies where the error has been found by only single proofreader, either A or B. So in this question, 5 error has been found by A only and 2 errors has been found by B only. So it's A only, right? This is A only actually, and B only has found only B only. This is B only. So you can see that if the null hypothesis is both are equally competitive, then both will actually find approximately equal number of error. So you can model it in terms of Bernoulli random experiments, right? You have a 7 tosses. If head occurs, let's say A is finding. If tail occurs, B is finding. So the probability distribution of the Bernoulli random variable with respect to coin tosses is actually getting translated to this particular scenario. So because your null hypothesis both are equally competitive, right? So just half times you say that A is finding A is actually finding the error. Half times you are saying B is finding the error. So your sample is given that 5 error has been found by A, 2 error has been found by B. Yeah, apologies for that. Here actually A is superior than B. It should be correct. That should be your alternative hypothesis. Okay. So what will be the p-value? So you have a Bernoulli samples with n equal to 7 and p equal to half, right? So you consider the y is some Bernoulli random variable with n equal to 7 and p equal to half. So you consider all such samples probability y equal to 5, 6, 7 as extreme or less extreme than the observed sample. So that will be your p value. Hopefully it's clear. The crucial part is actually model this in terms of Bernoulli experiment. So this is a comparative study, right? Hypothesis is actually comparing both things. Your null hypothesis says that both are equally competent, both are equally good, equally okay, something like this. And alternative says that somebody is good, better than other. So in that case, you actually model them as a Bernoulli trials as well. As number of error has been found by one person is higher, the likeliness that one is superior is also higher. Alternative hypothesis is A is superior than B. Please note that I have actually misspoke it earlier, so apologies for that. Okay, this is a linear regression model is there. Xi, yi as the training data. Epsilon is the normal random variable, standard normal random variable. Please see that as per the question, 0 mean 1 variance. And some data points are being given. Let's come to this later. Now beta 0 and beta 1 are the corresponding, let's say, maximum likelihood estimators. So it's important that we now calculate the maximum likelihood estimators. So please see that sigma is the normal random variable. Is yi is also random variable? Yes. So more specifically, yi given xi is also the normal random variable with one variance. It is important to note that yi given xi is actually normal random variable with one variance, and the density function is given by the pink bracket. This is my density function. Okay. Now, how to find the maximum likelihood estimates? You have n samples. You actually multiply the corresponding PDFs and you create the likelihood function. So that's what I'm doing next. I'm creating the likelihood function here. Okay. See, this is with respect to beta 0 hat and beta 1 hat. So okay. So beta 0 1 hat and beta 1 hat is different. So I want to maximize it for which data points are fixed. So yi, xi are fixed. You can also consider them as a training data as well. Okay. So this is a likelihood function and this is non-negative. So instead of maximizing this, I can also maximize the log of this. So 1 over square root 2 pi is actually always there. So I can also forget that. I can only consider the exponential part. Basically beta 0 hat and beta 1 hat are the variables. That's what I want to maximize. So you try to maximize it and you arrive at certain equation. So please see that the maximum of minus of this quantity is same as the minimum of this quantity, and 2 is also again you can ignore because after taking log this entire term will come into multiplication. So I am actually minimizing this, and this is exactly same as least square loss. There is nothing different. This is nothing but a least square loss. You are actually finding some beta 0 hat and beta 1 hat such that given your n training data points, this is actually minimized. This is nothing but least square loss only. Please see that. So maximum likelihood actually gets converted into the least square loss. How to do it? This function that I have indicated under the pink line, or let's say this green line, the green line function, you can del, let's say this is f. Okay, so you consider del f by del beta 1 hat and equate with 0, and you find the beta 1 hat star, del f by del beta 0 hat star, and you equate with 0. So you find beta 0 hat star and beta 1 hat star, that will be your minimum. Ideally you should find the Hessian. Everybody should know how to actually optimize the multiple linear regression. You find the corresponding gradient, find the Hessian. So ideally I should go by that particular context. Even if you go by that particular way, you will arrive at the same answer. But here I am actually deriving, making the partial derivation of this particular function equating with 0. There are certain reasons if I do this and if I do the gradient way, I will arrive at the same equation. But let's just try to partially differentiate this particular equation and equate with 0. So I am first of all partially differentiating with respect to beta 0 hat and equating with 0. You will see that beta 0 head star at beta 1 head star is related by this yi minus beta 1 head star. This is called as the average of xi's. This is given training data, it is fixed. Similarly, beta 1 head star also you can calculate. Now beta 0 head star you can actually replace with the y bar you can just say that a mean of the y's, x bar is mean of the x, beta 1 head star is there. Now you actually want to take the partial differentiation with beta 1 head and equate with 0. You actually simplify this entire equation and you will arrive at this particular formula. This is actually taking the partial differentiation with beta 1 head and equate with 0. You will arrive at this particular formula. And please see that beta 1 head star can be calculated using this formula. This is formula 1 and this formula 2, both are extremely important formula. You should know that. So given some yi's and xi's, you can actually directly calculate beta 0 star and beta 1 head star using this formula. Okay, this is formula. So this formula, if you want to remember, there is trick to remember. The numerator is sample covariance, denominator is sample variance. Sample covariance of x and y, and denominator is sample variance of x. That's how you can achieve the beta 1 head star. And once you find the beta 1 head star, you can actually find the beta 0 head star. Now you can obtain the bias term, whatever bias term also, optimum bias term and the corresponding slope of the line using this if you have this data. So this all the data has been given in the question. Please see that. You can just consider and simplify this. You will have the appropriate data given in the question. And once you have appropriate data, you can actually find the appropriate answer, beta 0 head star and beta 1 head star. It's important that you know this formula. Beta 1 head star is being given as a sample covariance of x and y, that is numerator. Denominator is sample variance of x. Beta 0 head star is the y bar, that is average of, okay, let me just write a beta 1 head star in the new line. It's becoming too messy. Basically I have arrived at using the maximum likelihood process only. So beta 0 head star I can achieve is y bar is the mean of the samples minus yi is basically minus x bar beta 1 head star. Beta 1 head star is the calculated from the above equation. Please see that. I will also arrive at the same formula. Just partially differentiate with respect to beta 1 head star and you will arrive at the same formula. You can just take the screenshot and you can try to do it by yourself. Please, I urge you to do it by yourself. You will see that you will arrive at the same formula. Okay. Thank you very much for watching this particular lecture and see you in the next lecture.